Hi, I'm Scott Knockley. In this video, we're going to look at the inverse displacement solution for planar manipulators. By the end of this video, you should be able to solve inverse displacement problems for planar manipulators. So we'll use the planar 3R manipulator to do an example of an inverse displacement solution. So for the inverse displacement problem, we would be given the position and orientation of the end effector. So we would know the x position, the y position, and we would know the angle alpha. So we can write this out. We'd be given x, y, and alpha. And what we're trying to find are the joint angles that will give us that x, y, and alpha. So we need to find theta 1, theta 2, and theta 3. So we previously did the forward displacement solution for this manipulator, and we showed that this is the solution for the x position, y position, and our angle, which was alpha. So in order to do the inverse displacement solution, we have to start with the forward displacement solution. Now, these are three equations in three unknowns. We have theta 1, theta 2, and theta 3, but you can see they're nonlinear. We have these cosines and sine functions. So to solve this system of equations, these nonlinear equations, we have to try different strategies. And there's no one way to do it, but there's different tricks we can try to make things so that we can solve them. All right, and first off, if we look at these equations, all right, we have C123 here and S123. We don't know what theta 1, theta 2, and theta 3 are, but we do know that theta 1 plus theta 2 plus theta 3 is alpha. So C123 is the same as C alpha, which is something we know. Likewise, S123 is S alpha. So we know C alpha and S alpha, and so now we've eliminated theta 3 from these two equations. So let's rewrite them. All right, and we're going to put everything we know on the left and everything we're still trying to figure out on the right. And we're going to create a new variable x star, which is what we know, which is x minus L3 C123. So we know x star. And that's going to equal L1 C1 plus L2 C12. Likewise, we can define y star, which is just y minus L3 S123, and that's going to equal L1 S1 plus L2 S12. And now we're going to number these equations. We're going to call these equations 1 star and 2 star. So now we have two equations in terms of two unknowns, theta 1 and theta 2. Now when you look at this, we have these trig functions. We got cosine terms and sine terms. So one trick you can try is squaring these two equations and adding them together and see if anything simplifies. So let's do that on the next slide. All right, so we're going to square and add equations 1 star and 2 star. All right, and that's going to yield x star squared plus y star squared equal to L1 squared C1 squared plus 2L1 L2 C1 C12 plus L2 squared C12 squared plus L1 squared S1 squared plus 2L1 L2 S1 S12 and lastly plus L2 squared S12 squared. So far it doesn't look too nice, but let's group our our like terms together. So we're going to have L1 squared, which is C1 squared plus S1 squared. We can group the L2 squared terms, which is C12 squared plus S12 squared. And then we can group the two L1 L2 terms, which is C1 C12 plus S1 S12. All right, so a little nicer, but still we need to see if we can simplify this further. So let's look at a little aside here. We're going to look at some useful trigonometric identities. Now the first one everyone's familiar with. We have cosine squared plus sine squared equals 1. All right, so we're going to make use of that. These two here, all right, these are useful if axes I and j are parallel, which for our robot they are. All right, all our axes are in the z direction, so they're all parallel to each other. So we can use these trig identities. So this would be cosine theta I plus theta j equals cosine theta I cosine theta j minus sine theta I sine theta j. All right, and then if you minus the two angles, you add them, and then it's a little different for the sine one. Okay, but we're going to make use of these in our robotics class. So it's important you have these written down and use them. So if we go back to our equations, all right, we can see right away we have cosine squared plus sine squared here as well as here. So we can simplify those. We know that that just equals 1, and this one equals 1. Now if we look at this term, it's C1 C12 plus S1 S12. Again, if we go to our trig identities, we have this trig identity here. All right, and what our bracket term there simplifies to is just C2. All right, so we have now L1 squared plus L2 squared plus 2L1 L2 C2. So we now have one equation in terms of one unknown, theta 2. So let's write that out again and see how we're going to solve that. So we have x star squared plus y star squared. Again, we know these two terms is equal to L1 squared plus L2 squared plus 2L1 L2 C2. Now you may want to try right away saying, well, I can do theta 2 is equal to the arc cos of x star squared plus y star squared minus L1 squared minus L2 squared all over 2L1 L2. The problem with a solution like this is arc cos only returns an angle between 0 and 180 degrees. Our robot joints can go, say, 0 to 360 degrees. So this solution here may not actually return the correct solution. Okay. So principal values are going to mess things up. All right, so we're not going to use that. Okay, so don't use. A better way to solve this to use, let's first solve for C2, which is x star squared plus y star squared minus L1 squared minus L2 squared all over 2L1 L2. And then we're going to use our trig identities, and we know that then that S2 is going to equal 1 minus C2 squared square rooted but with a plus or minus. All right, because when we have a square root, we have the positive solution or we can have the negative solution. So then our theta 2 solution then is going to be a tan 2 S2 C2, where a tan 2 is a quadrant corrected arctangent function. So a lot of programming languages, things like MATLAB, they have an arctan2 function. And what it does is it looks at the signs of these two terms. All right, and based on the sign, it returns the correct angle in the right quadrant. All right, so you'll want to use this arctan2 function when you do robotics. And one thing to note about this solution, because we have a plus minus here, there's actually two solutions for theta 2. So it's good to make a note of that when you do these solutions. So two solutions exist. All right. And if we were to jump back to our robot arm, all right, one solution would say be the elbow this way, but we could also have the elbow this way and get the same thing. Okay. So you can have multiple solutions to the inverse displacement problem. And we'll talk more about this as we do other examples throughout this course. All right, so we have two solutions exist, and we've solved for theta 2. But we still need to know what theta 1 and theta 2 are. Okay, so we can go back to our equations. Okay, and we can break these apart now, the C12, S12 terms, using our trig functions. So let's do that. So again, we're going to use these trig identities. So let's recall that C12 is the same as C1 C2 minus S1 S2. And we know that S12 is equal to C1 S2 plus S1 C2. So we're going to rewrite equations 1 star and 2 star now. So we're going to have x star is equal to L1 C1 plus L2 C1 C2 minus S1 S2. We're going to have y star is equal to L1 S1 plus L2 C1 S2 plus S1 C2. All right, so we did this in order to split apart the theta 1 and theta 2 terms. All right, because we now know theta 2, but we're still trying to solve for theta 1. So we can solve this, or sorry, rewrite these as C1 L1 plus L2 C2 minus S1 L2 S2. And we can rewrite this one as C1 L2 S2 plus S1 L1 plus L2 C2. So we'll call these equations 3 and 4. Okay, and if you look, these are two equations in terms of two unknowns, the unknowns being C1 and S1. So let's make a note of that. The above are two equations in terms of two unknowns, C1 and S1. All right, so let's solve these two equations with two unknowns. We're going to make things a little simpler. We're going to let A equal to L1 plus L2 C2, and we're going to let B equal to L2, S2. So equations 3 and 4 become C1A minus S1B equal to X star. And we have S1A plus C1B equal to Y star. We can put these in matrix form. So A, B minus B, A times C1, S1 equal to X star, Y star. This is going to be matrix A. And now we just solve this. So we can take the inverse of matrix A. So we'll do that. So A inverse is just simply going to be AB minus BA all over A squared plus B squared. So we know then that C1, S1 is going to be A inverse times X star, Y star. Okay. Which, if we multiply it out, is AX star plus BY star over A squared plus B squared. And we have BX star plus AY star over A squared plus B squared. So now we can solve for theta 1. So it's going to be the arctan 2 of S1, C1. Okay. Which is the arctan 2 of minus BX star plus AY star, AX star plus BY star. We can substitute A and B back into these equations. So we'll do that. We'll have minus L2, S2, X star plus L1 plus L2, C2, Y star. That's the S1 term. And get something similar for the S2 term. Okay, and so that's our solution to theta 1, and there's just one solution for theta 1 for whatever solution of theta 2 we're using. And then the last thing we need to solve for is theta 3, so if we jump back to the equations, all right, we can just simply use this third equation to solve for theta 3 very easily. So we know that theta 3 then is just going to be alpha minus theta 1 minus theta 2. So that is our inverse displacement solution for the 3R manipulator. And you can see there's up to 2 different solutions. All right, and we talked about you can sort of have an elbow up and elbow down solution.